This video explains the superposition theorem, which can be used to analyze circuits with multiple batteries and resistors, but without relying on Kirchhoff's laws. The superposition theorem is versatile, and you can apply it to solve circuits with multiple batteries as long as you know how to analyze single battery circuits using equivalent resistance. The superposition theorem says current in a circuit with multiple batteries is equal to the sum of the currents produced by each battery separately. I will not prove the theorem, but just briefly, the theorem works because in a linear circuit, the voltage across or current through any part of the circuit is just the sum of the contributions from each source acting alone. We will consider this circuit, which has 2 batteries and 3 resistors. And to make our discussion concrete, we will assume these values for the voltages for the batteries and the resistances of the resistors. Our goal is to determine the 3 unknown currents in the circuit without using Kirchhoff's laws. To make it easier to follow, I will label the 24-volt battery in red and the 6-volt battery in blue so you can clearly see the contributions from each one as we apply the superposition theorem. Let's first consider the contributions from the red battery. We replace the blue battery with a wire, which effectively removes its influence on the circuit. In this case, the 6 ohm resistor in the middle and the 3 ohm resistor are in parallel, and after some math, we can show that the equivalent resistance is 2 ohms. And the combination of these 2 resistors is in series with the 6 ohm resistor in the bottom left section of the circuit, making the equivalent resistance of all 3 resistors equal to 8 ohms. Using Ohm's law, we find that the current from the red battery is 3 amperes. The battery is in series with the 6 ohm resistor in the bottom left section of the circuit, so the current through it is 3 amperes and it flows to the left. This current splits between the 2 remaining resistors based on their resistances. Since the 3 ohm resistor offers half the resistance of the 6 ohm resistor, it allows twice as much current to flow. That means 2 amperes go through the 3 ohm resistor and it flows to the right, and 1 ampere goes through the 6 ohm resistor in the middle of the circuit and it flows downward. Let's now consider the contributions from the blue battery. We do this by placing back the blue battery and replacing the red battery with a wire. Using the same approach as the previous case, we find that the equivalent resistance of the 3 resistors is 6 ohms, making the current from the blue battery 1 ampere. This makes the current through the 3 ohm resistor 1 ampere, and it flows to the left, and the current through the 2 6 ohm resistors 0.5 amperes each, as shown here. Having calculated the contributions from each battery separately, let's now consider their total contributions. For the 3 ohm resistor, the red battery creates 2 amperes of current flowing to the right, while the blue battery creates 1 ampere of current to the left. So the actual current that flows through the resistor in the presence of both batteries is 1 ampere to the right. For the 6 ohm resistor in the middle, the red battery creates 1 ampere of current flowing downward, and the blue battery creates 0.5 amperes of current also flowing downward, making the actual current 1.5 amperes when both batteries are present. Lastly, for the 6 ohm resistor in the bottom left section, there's 3 amperes of current flowing to the left, which comes from the red battery, and 0.5 amperes of current flowing to the right from the blue battery. So the actual current when both batteries are present is 2.5 amperes to the left.